All right, we are now also live on YouTube, and I will drop the link here in the chat.
Okay, thanks a lot. It sounds great.
Sure thing.
So then let me slowly start. Welcome everybody. This is the Zero Knowledge Learning Group, which is practically a meetup serial from Linux Foundation Decentralized Trust. And then today's topic is like advanced circum programming. I mean, it's not necessarily gonna be like absolutely advanced, but like it's gonna be like more advanced than last time practically. And my name is Daniel Szegő. I'm doing this meetup series. So let me just jump into some introduction and some logistics. So this is the Zero Knowledge Working Group. It looks that way that we organize this learning group once a month throughout 2025. It's always on Thursdays. Usually we try to keep or try to have the third Thursday of each month. It's starting from 6 o'clock in the afternoon, Central European time, which is like 9 o'clock Pacific, if I'm not mistaken. And then, yeah, probably 1 o'clock in the afternoon East, so something similar. And the logistics looks that way. So we try to keep these sessions, these meetups short, which means 1 hour top. And then it looks that way. I'm doing practically a presentation, sometimes with some demo coding, and there might be a short discussion at the end. We don't always have the time for discussions, but basically there's like a Discord channel. I'm gonna show it in a second. So basically I would encourage the participants to have the discussion on the Discord channel. Because again, so the main idea that we just keep these learning group sessions practically small, or as small as possible. We are covering different topics on zero knowledge proofs, mostly from software developers, programmers, and application developers' perspective, with some theory. So I'm myself not a mathematician. I'm rather a software engineer. So we already covered some theory, but practically we cover things more from a, practical application developer's perspective. So the coordination is on Discord. There's a Discord channel for Linux Foundation Decentralized Trust. This one is the link for that, but basically, if you're just Google or if you're familiar with like Linux Foundation, you can just Google for Linux Foundation Decentralized Trust Discord channel, or you might as well find actually on the Linux Foundation Decentralized Trust site as well. And if you join to the channel, we got like a sub channel, which is somewhere under communities. And the last part of the communities is practically the Zero Knowledge Learning Group. So we are basically here. I will post practically everything on this channel. And well, I mean, supposing we don't have like time for discussion, or sometimes not even like answering questions, I would encourage everybody to have the discussion practically, I would say, off chain. So somewhere here, and then I will try to answer as many questions as possible, as fast as I can, basically. And then I would encourage practically that perhaps there's like a discussion which doesn't necessarily involve just me, but like, if some or few other people is discussing zero knowledge proofs and the zero knowledge technology, that could be like awesome as well. The meetups are on meetup.com. So it's classical Linux Foundation Decentralized Trust. We got a meetup.com, and practically, as this event is practically decentralized online, so it's not related necessarily to one regional settings. These meetups are practically replicated throughout all the meetup.com locations of Linux Foundation Decentralized Trust. And all the content is practically covered and administrated in a repo. We already managed to set up like a lab that's like a Linux Foundation Decentralized Trust lab, and we are there. So basically, if you go to link to GitHub, you're gonna find Linux Foundation Trust Labs, and under Linux Foundation Decentralized Trust Labs, you're gonna find a ZK Learning Group GitHub repository, and that's practically all the contents that's possible. So basically, what we have, it's anything special. It's like practically the whole logistics, all the links to the meetups, to the repos, to the slideshows, and so on and so forth. And you're gonna find practically all the demo code here as well. So that's what we do practically. And if you are not familiar, then basically Linux Foundation Decentralized Trust Lab, that's like a small GitHub project. So it's not a full-scale lab. It's like something small, basically, which is evolving over time, and it's totally open source. So you might as well, replicate it or fork it or even contribute if you want. And then that's the main logistics. We're gonna do it until practically December. There's always like small challenges, sometimes quizzes, sometimes programming challenges. So if you're very keen, and then you can send me the solution for these challenges, then there might be some Linux Foundation Decentralized Trust merges at the end of the year. So that's the roadmap for the year. We started somehow in February with introduction, with theory, with some definitions and building blocks. Then we covered polynomial commitments in March, some interactive oracle proofs in April. This was more like the theoretical basis, or one of the theoretical possibility to build up a zero-knowledge proof. And then we just continued with circum basics. Circum is a zero-knowledge programming language, and we cover more advanced circum practically this time in June. And then we will probably continue with another zero-knowledge programming language next month and in August as well. So practically during the summer, that's SNARK. And from September, we just try to cover more like application development topics. So like classical zero-knowledge applications, which is like an off-chain transaction or a private transaction. It's like something which is like proving solvency or proving reserve, like in an exchange. Then some ZK rollups or very basic ZK rollups practically in November. And then in December, we make kind of a wrap up, and then we demonstrate just, I don't know, a few more applications. But this is just a general idea. I mean, it's subject to change. So if you prefer any kind of topics in zero-knowledge proofs, just give me a note or send me a direct message, and then I can just take a look if I manage it from a conceptual point of view, or put into the agenda of these zero-knowledge learning groups throughout the year. So that's the agenda for today. I'm always having like 2 slides as a summary. It's just because perhaps it's boring in a sense, but I would say as basically zero-knowledge is such a complex topic, it's just not bad to repeat, like at least in 2 slides, the previous content. So practically, I'm gonna start with ZK SNARK. I'm gonna continue with circum as a basic summary, and then we continue with programming in circum. Then we just cover circum league. I have 1 slide, a little bit more on the details of power of tau, some tips and tricks. We're gonna have a demo, and as usual, we continue with links, resources, challenge, and if you have time, with some questions and answers, Q&A. So let me just start with like SNARK or ZK SNARK. So basically, first, we are having a model, if we speak of like zero knowledge proofs, SNARK, ZK SNARK. We got like two rows. I mean, similarly as in cryptography, Alice and Bob. It's just not necessarily Alice and Bob, but we're gonna have one row which is a prover, and another row which is a verifier. And basically, the prover tries to create a proof on something, usually on a function or on a computation. And then this proof is usually, I mean, has a few properties basically. It is usually a small proof, like on a complex computation, and it might hide a few like inputs. So that's what basically a proof, and that's what basically a zero knowledge proof. To go more like into the details, if we cover zero knowledge proof, we usually have like a domain that we want to create a proof from basically, and this might be a computation, or this is usually a computation or a predicate. A predicate is a statement on something, but even a predicate can have a kind of computation behind. And if we speak of like zero knowledge proofs or SNARKs, this computation is like a little bit tricky. We usually have something which is like a little bit abstract. We usually think of computation as arithmetic circuits or kind of constraints, polynomial constraints or something similar. But having like an arithmetic circuits, we might as well say that we get like a more precise computational model. We're gonna have like a C function which has like two inputs, and then it produces like kind of a computational result. And the important thing is that one input is like X, that's like a public input, so it is well known both for the prover and for the verifier. And we have something which is a private input, which is W, and then W is known to the prover, but it is not known to the verifier. So that's like our basic computation model. Usually, if we program zero knowledge, we have like a life cycle. Usually, we start with a high abstraction computational model, not necessary from arithmetic circuits. That's gonna be compiled to arithmetic circuits. That's gonna compile to polynomials, and then basically polynomials gonna give us basically the zero knowledge properties that we need. So being more precise, we usually have like two algorithms. I mean, as we mentioned, we got prover and verifier, or Alice and Bob. But in cryptography, these rows are usually not people, but like algorithms. So basically, we got like two algorithms, one algorithm for prover, and the second one is the verifier algorithm. So the prover algorithm gets practically the public input, the private input, and creates a proof. There's like one parameter here, which is kind of a preprocessing step. So we might need like a preprocessing and then create some preprocessing argument before we can create proofs and verify the proofs. And these preprocessing arguments will be both in the prover algorithm and in the verifier algorithm. So this PP and VP are like the preprocessing algorithms. But supposing we have the preprocessing, then the prover algorithm takes the preprocessed parameter, the input parameter, the private parameter, and creates practically a proof. And the verifier algorithm takes as well a kind of preprocessing argument. It takes only the public input, it takes the proof, and it either accepts or rejects this proof. So that's practically the verification algorithm. And then actually this whole structure has like a few properties, which is like important in SNARK or zero knowledge. One is succinct. Succinct means practically that the proof is small in size and small in the verification time as well. So practically this is important that we can use in blockchain, because like, we don't want to store many data or much data in the blockchain. And then if we verify something with smart contract, that should be verified pretty fast due to the limited block size. It should be complete. So practically, if if there's like a private input which is known by the prover, then there can be practically a proof generated which will be accepted by the verifier. It is knowledge sound as well. So if that's the other direction, so if there's like a proof which was generated by some prover, then there must be practically a W secret input or witness which is known by the prover. Otherwise, this proof could not have been generated. That's like knowledge sound. And we got one property which is zero knowledge, which means that basically this proof I mean, just having this whole interaction and then the proof, basically, there cannot be revealed anything on this private input. That's zero knowledge. And we got one more parameter, which is usually non-interactive. So in this setup, the prover just sends the proof to the verifier, but we can imagine like more complex protocols as well, like sending something from the prover to the verifier, answering with some parameters, sending one more input, answering with something else, and so on and so forth. It's possible. It's called the interactive zero-knowledge protocols. Of course, we focus on blockchains. In blockchains, we don't like interactive protocols because we don't want to have like many interactions with the blockchain. We just want to create one proof, verify it on the blockchain, store it on the blockchain, and that's all. So we like it basically non-interactive, and that's the reason of sussing non-interactive argument of knowledge, which might be zero knowledge or non-zero knowledge. So that's like ZK SNARK. Then we got like circum. Circum is a programming language and a zero knowledge programming environment as well. It's just, again, basically, we don't like programming like arithmetic circuits very much on a low level. And we don't like programming with polynomials either. So for this reason, circum is a tool more like for programmers. It's a domain-specific language for circuit programming, and it's practically a development environment as well for arithmetic circuits and constraints. It was used like in the famous or unfamous tornado crash. It supports like two different cryptographic primitives or zero-knowledge protocols. One is Gross16, another one is Plonk. It's pretty well established, like exists already 3 years, which is, yeah, pretty old, I would say. And it supports like few interactions, like with JavaScript, C++. There's like even a solidity verifier as well. So this is like the high-level architecture. Basically, if we want to program with circum, if we want to develop something in circum, then usually we start with a higher level circuit description. So that's our program. That's going to be compiled by the circuit compiler to a lower level circuit. Then basically we get as we have like the lower level circuit description, we can basically set up our proof. So basically there will be like a setup. It's going to be like a trusted setup. It's going to be a trusted setup which should be executed once for Plonk, and there will be like another one which will be executed pro circuits for Gross16. But basically this is like a setup, and based on the setup, we got like proving keys and verification keys, and basically based on our computation key and proving key and our secret and public input, we can create the proof, or we can generate the proof actually with the circum environment. And based on our verification key or validation key and the generated proof and the public input, we can basically verify our proof. So that's the idea for circum. And let me just continue. We took a look on a very basic level last time, but let me just jump a little bit more into the details of circuit. So circum basically is kind of a hardware description language. It's just funny to say basically, sorry. So it's not like something which is an imperative language. It's not like a normal language. It's pretty similar to a hardware description language, as you like program like, physical hardware or physical circuits. It's just, it creates like abstract circuits, which we do again, not like physical circuits, but kind of a special abstract programming circuit. The basic element for circum is the template, is the so-called template. The template is basically kind of an abstract circuit that can be from this abstract circuit you can make practically an instance basically, and then it looks that way that this abstract circuit can have like input signals, output signals, and some internal signals as well. There can be like public and private inputs, but it's not necessary specified for templates, but it's specified more like for the whole circuit. So again, if you just specify a template, that's gonna be like an abstract circuit, something similar as an object, and to have an exact like non-physical circuit from this template, you just make to create an instance from this template. And if you create an instance, then it can be specified of like a signal is input or output. The only difference is between like a physical circuit and this abstract circuit is that we don't create like exactly circuits, but instead what we create is more like rank 1 constraints. So rank 1 constraint is like A times B equals C, where like A, B, and C are linear combinations of variables. So basically, we have like one expression which looks that way, which is like a constraint. So usually we define in circum like constraints, not really like circuits, but like kind of an arithmetic circuit, which looks that way. And for instance, this rank 1 constraint says that A times B must be equal to C. So if you just take a look, basically, our demo, let me just take a look. The last demo that we had just one demo, which was like a cube operator. So at the end of the cube operator, it looks that way. We had like one template last time, which was an abstract demo one template for an abstract circuit. It had like two input signals, which was input A and input expected cube. We had like one signal, which was an internal signal, which was calculation, and we had like one output, which was like cube. And if you just take a look at the last statement of this template, of this abstract circuit, it says the expected cube must be equal to cube. So that's like a constraint, actually. We could have like some multiplication or addition here as well, but this is like a very simple form of a constraint. So that's what we can have. And then there's like another operator as well, which is like different a little bit. It's more like not a constraint, but a calculation. So we can say that basically, if we have this format, that we can say that, hey, the value of C should be A times B. That's like setting value of a circuit practically, or of a signal, sorry. And then what's perhaps more important, we usually, so what we want to have, usually we want to have like constraints, because that's the core of like creating a proof. We don't really like just setting values. So generally, what we say is that the value of C should be like A times B, and we just want to create like a constraint on that as well. So making sure that actually there should be a rank 1 constraint as well, that C is equals to A times B. So for these two operations, we have just this arrow equals equals. It basically means that like here the signal of calculation, the value of signal of calculations should be like A times E. and it should be both basically as setting value, and there should be like a rank 1 constraint generated for this one as well. So usually that's what we use. In a lot of cases, it's like, again, setting value and creating basically a rank 1 constraint on that. And that's like our main operator, I would say. Anyway, signals are basically integers. These are like 255-bit integers, positive integers. So like if we need to use like, rational numbers or something, we have a limited possibility, basically. So again, this one is a template. We use just the demo key, the template keyword, and basically we just created like an abstract template on that. What's perhaps important to note or to recognize, so this is like always at the end of the day, it's always like even if you say like templates, so we have like one template here, but we just have to create like an instance on that, and this instance should be always similar to a physical circuit instance, basically. So if you have this like main component, what we basically do, we just create one instance from this demo one, and it's like one circuit. So something similar, which is like a expected Q calc cube. So it's something similar as we say here. Let me just try to draw somewhere. So you should always imagine that basically at the end of the day there will be like one physical circuit generated, and we have like the inputs E, that was like expected Q, cube, and we have like one output here, and we had one internal signal as well, which was a calculation, if I'm not mistaken. But again, so this is like one circuit somewhere at the end of the day. So we can initiate a circuit with a component keyword, and then we should always have like a main component, which is like the main calculation. Yeah. So the next one is that we can have more than one circuit. And then let me just go to my demo. We have here just one circuit, one just template. But let me just take a look on my other demo. So basically what we are having here is basically we have like two templates in one file. We have one square template, which has like one input signal and one output signal, and it calculates basically the square of the input. We have like two internal signals as well, greater and is null. And basically, I'm just skip this code, but basically we have something which is like, out should be equal to input times input, which is like a square functionality. But the point is that in a file we can have more templates as well. And basically, if we have more templates, we can have two options combining these templates, these circuits. So one is somehow, I mean, the classical way is wiring. So we can have this calculation here. This was like a calculation. And then we can have another circuit as well, which can be a pretty similar calculation. And it can have like input signals and then some other input signal and some output signals as well. And what we can do, we can really wire these things together. So basically the output of one initiated circuit template should be equal to the input of another initiated circuit template. And then basically this way we can just wire several different circuits, arithmetic circuits. So somehow this way. This is one option. And the second option is basically it looks that way. Let me just try to delete this guy here. Is to embed one circuit in another one. So basically what we are doing here, I have one calculation, and basically as I define this calculation, again, usually I just use these operations that the value of A should be equal to B times C plus 4 or something, which is both a setting operator and basically an arithmetic constraint as well. So that's how I define basically the internal logic of my circuit. But what I can do, I can embed a circuit as well in the calculation as well. And I can say that this is like something which is defined in another template, which is a circuit. It has some inputs, some outputs as well. And like this input should be equal to A, for instance. And like this output should be equal to C or something. So this is like an embedded circuit. Okay, so that's generally how we create our logic. That's how we create our programming model, basically. So going back to the example, I got here something which is a sum of square. And the sum of square looks that way. I just want to, I have like two inputs, which is like A and B. I have one output, which is like out. So basically what I'm doing here is that I just want to have like A square and B square, and I just want to sum these A square and B square. And I could just directly create in the logic. But what I'm doing is basically I use like embedded circuits. So with the component keyword, I just initiate basically the square template, the square circuit as SQ1, and then just create an instance from this template a second time as well, which is like SQ2. And what I'm doing here is like I'm just wiring these things. So basically, it's like one component, which is SQ1. It has some inputs, it has output basically. So I can just refer basically to SQ1.in, which is the input. I just said that basically this should be the same as the input of my sum of square circuit. I set like the input of this SQ2 component, which is again a square, which has one input, which is in. And then I just said basically that the input of this component should be equal basically to the input of my sum of square component. And then basically I have one more constraint, which is like the out. So the out, which is the out signal of my sum of squares component, should be equal basically as the sum of the out of the SQ1 component plus the SQ2 component, basically. Okay, so that's how I use practically embedding, and then it's more like wiring as well in a sense, basically. Okay, so that's how I use basically that's what I do in programming in circum, and that's how I program basically arithmetic circuits. It's just, as you might recognize, it's not kind of a very high level programming language. So basically, if you want to program something complex with this setup, it's pretty far from being simple. So basically, what we have here is something which is another programming tool, which is like kind of a meta programming. Again, it's just pretty tricky, but if we have like meta programming, it's similar if you ever programmed like hardware description languages. That's practically the same idea. So we have to pay attention that at the end of the day, or at the end of the compilation, we will always create like one big circuit, which looks that way. So it has like input, outputs, and these inputs and outputs are wired somehow. But just for to write less code for creating this pretty big circuit, we can use something which is meta programming, covering like variables and meta programming elements as like loops, if thens, and so on and so forth. So What's important is that like we can have like a variable, but it's not part of rank 1 constraint, and then we just can't use it in rank 1 constraints with signals, and then basically it's sometimes it's just pretty tricky to use. Again, variable is kind of a meta programming level which helps you create like one big circuit with like signals and wire signals, but basically it's not part of signals. So we can create like a variable with like a var keyword, and it's important to note if something is a variable or something is a signal. Again, these keywords are different practically. And we can have like different assignments as well. So we can use like variables in a normal way, as like in a C syntax, and assign variables as we want. But it's important to note that just based on the variables, there will not be practically rank 1 constraints. And at the end of the day, we need to have like rank 1 constraints to express our logic. So let's just take an example, take a look on an example. So we have here something which is a sum of square. Sum of square is like a more complex template. It has inputs and it has outputs as well. And then we indicate clearly that we use like inputs and signal. And basically, if we use inputs, we can use only signals as inputs. But in the middle, we can just create something more in a more compact way, so we can have like variables as well. And as soon as we have variables, they are indicated clearly with this var keyword. So that's how it looks like. In meta programming, we can use like loops, we can use if-thens, but again, it's important to note that basically there will be one big physical circuit, rank 1 constraints, or rank 1 circuit, and everything is fixed size basically. So we can use template arguments and circuit arguments as well, and even functions. I don't have like functions in this example, but what I'm having here is just take a look. Basically, we have something here which is a sum of square, and sum of square is a template which has one parameter. So basically, what I can say that I want to just sum the squares of like 10 inputs. And 10 is the parameter, and I can basically create such an abstract template. But it's important to note that this parameter should be fixed as soon as I create my circuit. It's just because you have to pay attention that at the end of the day or at the end of the compilation, there must be like one big physical circuit. So basically, this parameter should be initialized with an exact data. So, but nevertheless, this is like an abstract template, and we can use something which is like practically arrays. So as you see, basically, we have like here not just one input signal, but like an array of inputs. And that's like, it's like, it looks as a classical array, so it's nothing special. It's again important. Basically, we can have only like fixed sized arrays of inputs. It's just because everything is fixed sized at the end of the day. But what I'm having here is like the same parameter. So what we can do here, basically, I have like one template, which is a circuit template with like one parameter, which is input parameter n. And then if I just set this n, then the same parameter will be used as for the input size as well. So practically, if I just want to use the sum of squares for 10 inputs or 10 squares, summing up 10 squares, then basically there will be the same 10 value used for this array as well, and it will be like a 10 long array. And again, I have some more components which is more like arrays. And then it's pretty much the same. So basically here I'm having like an array of components, which is again uses basically this m parameter. And here gets tricky. So what I'm having here basically, I have a few variables, and I'm having one loop. and this loop is practically used to create n pieces of different circuits. So basically, what I'm having here, I define my components as an array, and what I'm doing here, I just create this square circuit n times. I just set the input values of this square circuits again n times. I just use the output of this circuit, of the nth circuit practically, and then just sum up everything into a variable, basically. So again, this is like a summing up of like n squared circuit, again with like a loop, which is kind of a meta programming, and then basically there will be like 10 different circuits generated if I initiate this whole structure with n equals 10. And then at the end of the day, what I do is what is expected. So I said that the sum should be equal to the output, and then basically the output should be equal to the expected output. So again, this loop practically generates in a physical world, or like more in a abstract rank one constraint circuit field, where like n pieces of different sum or square circuits. Okay, so this is like a little bit tricky, and at the end of the day, what I'm doing is, of course, so I cannot leave that thing in an abstract way, just having by n. So basically, I create my main component, which is like an input component of this source structure, and I say that, hey, this should be like the sum of squares, and I should initiate with 2, or I initiate it with 2. This is like, I just need like 2 pieces of squares, basically. That means like 2 different circuits. So that's basically the idea. Yeah, again, so it's not necessarily so easy to program in circum. And there are even like simple structures that are not so trivial, I would say. So for this reason, there's like a cool library, which is like a circumlib, which contains a lot of like, best practice and typical templates. So basically, if we just take a look, it's on GitHub. So we can just take a look. Practically, that's like the circumlib, and then it contains a lot of like example circuits. So if you just go in, we have like very simple circuits. These are practically like gates like AND, XOR, or NOT, and so on and so forth. But we can have like what's practically is practically comparisons, if I'm not mistaken. Yeah, that's like comparators. These are again like sometimes a pretty easy logic is difficult to grab in circum. So we have like is 0 or is equal or greater than or less than logic, and so on and so forth. And we have like cool things on a cryptographic side as well. So we have like cryptographic primitives, like thing that's like Pedersen commitments, if I'm not mistaken. We can have like elliptic curve digital signature. We have like Poseidon here. Poseidon is like a hash function, and then we have some other cool material as well. It's like EDDSA. It's not ECDSA, but it's EDDSA. It's again an elliptic curve digital signature. So we have like a few options here to use, basically, or a few modules here to use. So again, that's what circumlib. Again, it's practically different practical pre-programmed circum templates, and starts from the basics, like basic logical gates, bit operators, is0, multiplexer. I mean, sometimes in programming with circuits, like an if then is sometimes tricky. So we have something which is switcher, less than, greater than, and so on. And we have like a few cryptographic primitives as well, like the EDDSA, that's like the Edward curve digital signature algorithm. We have like hash functions, MIM, Pedersen, Poseidon hash function, and even SHE 256. Perhaps it's worth mentioning, the problem is with the cryptographic primitives, that some of the classical cryptographic primitives are not very zero-knowledge friendly. So like, especially like a classical elliptical digital signature algorithm, ECDSA, is difficult to program in circum or even in zero-knowledge program in programming. It might contain like a lot of different circuits. So for this reason, we usually find in zero-knowledge programming libraries ZK-friendly cryptographic primitives. And then if it's our design choice, then basically we should use these primitives if it's possible. So again, like the Poseidon hash function is like, which is like circum and zero-knowledge proof friendly. SHE is not so zero-knowledge friendly, for instance. And I have just one more slide practically on the power of tau. We mentioned last time, but again, I just wanted to emphasize. So the problem is usually that we have like trusted setup, and then especially for Gro16 and Plonk, we have like per circuit or universal transparent setup, and then there's like basically a multi-party computation ceremony to set up this trust, this central trust. So it's like practically generating parameters for zero SNARKs, for ZK SNARKs. And usually there's like multiple participants contributing this randomness. And the reason is for having these multiple participants, that basically if one participant acts honestly, then the resulting parameter should remain actually secure and confidential. So again, even if we say like trusted setup, it could be like made like, I mean, less trusted practically. So tau refers here like a secret value or trapdoor used in the parameter generation process. And in we took a look last time, but basically there's like the SNARK.js, and SNARK.js, that's a JavaScript library, has some like built-in functions with power of tau. So we can create like power of tau, we can create a new such a tau or such a secret, and we can just contribute several times with like random values. And again, if we just consider several contributions, then even if one contributor is honest, then the result will be randomized enough. So just showing two things on the code. Basically, what I wanted to show first in the code, just back to the circumlib. In this code, we just imported basically circumlib. Again, that's the library that I mentioned. And we use just, I mean, we don't really use it, I just integrated it, but we use like two elements from this comparators, from this circumlib library. I use two from the comparators.circum, and then I just use a greater, equal, or equal than, and then is zero practically. And then I use it in a normal way. So basically, I just initiate a component based on the circuit, and then basically I just wire the inputs and the outputs of this circuit, and then basically that's all. So that's one thing. The second one, I'm just gonna show it basically. If we just generate everything, we have like a lot of commands in our setup procedure. But basically, if we take a look, we have this power of tau commands. So basically, I have like two phases for generating this power of tau. One phase is like a general setup. And if I use like row 16, I just have like a second setup, which is like a pro circuit setup. And basically, I just use this SNARK.js JavaScript library, or that's installed at the moment for me. So it's more like a command prompt. And I just use these two commands like power of tau new and then power of tau contribute. And that's for the second phase. And for the next phase, we got some pre-prepared commands as well, like prepare the second phase, and again like contribute the second phase, and so on and so forth. So with that library, you can build up like, more complex power of tau setup ceremonies, like having like, I don't know, 100 of different contributors. So a few tips and tricks. If you start programming with circum, it's just sometimes difficult to distinguish between variables and signals, like comparison, like if dance. So it's usually, I mean, you need some practice with that. I mean, the security circum is like something which requires some considerations as well. Usually try to use this setting value and setting constraints together. If you use just setting value for a signal, then make sure basically that you have the constraints as well. Just take a look on optimizer considerations, and then yeah, performance can be another issue as well. Basically, if you have like too many constraints, then things can be pretty messy. And then for testing and debugging, there's like a log command. So basically, I have just one example on that. So basically, you can use like a log, and then it logs some of the inputs and outputs as you, or even variables as you just create a proof. So it's a good idea to debugging basically, and then basically you can even create like unit tests. There's like a separate GitHub library for that, creating like unit tests in Mocha and Sky. So I'm having the demo. I already show a lot of things, I would say, but let me just take a look and run that. I hope it's gonna be run. So this is like a sum of squares, with like, you know, two elements as I show. So again, it's just taking a while because there's this power of setup ceremony which uses like a lot of cryptographic elements. It's like I mean, especially like fast Fourier transformation is something which is just taking time, but I hope it's gonna be finished. But again, that's what I'm here running. I've just got sum of squares. I have some inputs basically, which is like, you know, just 2. It's like 2 inputs, 2 and 2, and then 2 times 2 is 4, 2 times 2 is 4. So basically the expected input should be like 8. And honestly, I'm not so sure which one was like the, yeah, it was just the input was like the public input was the A, and for some reason the expected output was like the private input. I'm not quite sure what was the reason again, but you can just play with that. So that's what I'm generating, and I'm just creating a proof on that. So basically, it's still the power of Tao's ceremony, but as soon as I finish, basically, then based on my scripts, again, which looks that way, that it's summarized in run.js, what I'm having, I'm just setting up basically everything. I will create after the setup something which is like a proof with like create proof, and then basically I will verify the proof as well. So that's what's basically at the end of the process. So it's still running. Probably it's just 1 more minute and it's gonna end. So in the meantime, let's see what I missed. So basically, we covered like templates, circuits, components, wiring, variables, loops. Again, that's like our templates arguments. That's like the metaprogramming. I mean, constraints, that's like the core elements, logs and tests, basically just for debugging and logging elements. Perhaps it's one thing. Let me just check. It's still running, but probably it's gonna be finished. I mean, already the proof is generating, and the verifying is running as well. So it looks great. So basically, if we just go inside, we should have like a proof. So this is like a proof that we have our computation and with some inputs, and then the public inputs are actually all free. Yeah. I need to double check it if that's what I wanted to, but again, I just initiated in a pretty random way, basically. So one more thing that I would like to mention, you can of course combine these circum files into 2 files. So if you have like a pretty big file, you can do it in a way that practically you create a library, and then basically based on the library, like, I mean, just let me just imagine this one is a library having like 3 templates, like square, sum of squares, and sum of squares m, and you can create as a you can say that's a library. So you don't create basically on the same file a main component. Instead, you can create like for each file, basically a different file with a different main component. And basically you can test these templates one by one. It's just probably more work, but it's better than, or it's easier than to debug things. Anyway, perhaps I can even show that basically if you take a look on the generated output, that was somewhere, yeah, that was the log. So that's the log. It's like the cycle 0 partial sum 4, cycle 1 partial sum 4. So that's like here the log component. Again, it's not so easy to debug. So I would say sometimes the best idea is just having these circuits one by one and test them one by one. Okay, so that was basically the main part. I get like one developer challenge for the next 3 weeks or 4 weeks. It's just create a circum implementation for a simple 3x3 Sudoku. And then how the Sudoku works, it's, I don't know, there are like, I don't know, probably 1 or 2 options. Just feel free to implement anything that you want, which is like similar to a 3-to-3 Sudoku. And I have some links, resources, and literatures at the end. And I still did not check in to the GitHub repo, basically this example, but I'm doing it today, so in the next 2 hours. So you will find all these example codes in the GitHub repo as well. So that was all for today. Perhaps we're gonna have like time for one fast question. Because we are just running out of time a little bit as usual. But again, generally, I would encourage to use basically the Discord channel to have questions or discussion. So if you have like one very fast question, I'm gonna try to.
Presentation. I wanted to ask you how you will handle a simple conditional case like if else. Like, can you give a simple example? How would you approach something like that? Because without that simple construct, it will be complicated.
Yeah, so it's more complicated because, I mean, again, if then is usually not something which can be directly used because it's like a meta programming. I will usually what you use is something which is like a multiplexer. If you are familiar with like digital circuits, you don't have like digital circuits, but like you have like multiplexers, for instance, or you can have like there are comparators here as well, which is like which is again tricky sometimes, but like is 0 or is equal then or less than or equal than. So these are the sub-circuits that you can use, and again it can be pretty tricky to build up your whole circuit that have conditions. But usually if you use like simply variables and metaprogrammings, that's not gonna work. You will find a lot of errors because you just can't assign variables to circuits and vice versa in a pretty free way or a pretty flexible way.
Thank you. Yeah, a multiplexer answers my question. I mean, depending on the input, you will have different bits set to different signals at 1 or 0, depending on your condition. So it allows you a bit of a switch construct, so to speak.
Yeah, again, I will try to put some examples in the Discord channels then. Okay.
Thank you.
Okay, so I would say that was for today, and then well, we're gonna continue in 1 month. The plan is with that with some NOR programming. I hope I will manage to prepare the topic, but anyway. So thanks a lot for the attention, and again, thanks a lot and happy hunting for the SNARK, and then see you practically next month.